Everyone, thanks for joining us. I am Caleb Kinchlow, and I'll be your host today. Today's event is from D-Zone and Fairwinds. Our topic, running LLM interference on Kubernetes, a reliable path from cluster to first prompts, particularly using EKS. Now, before we jump in, just a couple quick notes. This session is being recorded and we'll share the on-demand version afterwards. And if you have any questions, feel free to drop them in the chat, and we'll get to as many as we can during our Q&A portion. Well, as more teams look to run LLM inference on Kubernetes, getting from a cluster to a reliable working endpoint can be more complex than expected. So today we'll walk through how to make those processes more practical and production ready on EKS. We'll cover what these workloads need from Kubernetes, along with some of the common challenges and how to get to a working inference endpoint. All right, so with that, I'm excited to introduce our speakers. First, Andy Sutterman, CTO at Fairwinds. He helps organizations adopt and operate Kubernetes effectively and is the creator of Goldilocks, an open source tool for Kubernetes optimization. He's joined by Stevie Caldwell, senior tech lead at Fairwinds. She leads a team supporting microservices on Kubernetes in AWS and brings hands-on experience managing production scale environments. Andy, Stevie, thanks for being here with us. I'll let you take care of it.
Awesome, thank you. It's great to be here. As Caleb said, we are from Fairwinds. That's our company. And then on our next slide, tell you about our company mission. I do not believe in reading slides out loud to people, so I'll just summarize and tell you that we are a company that helps people, become more efficient with their Kubernetes infrastructure. So, help them create these clusters and manage the clusters, take away a lot of the overhead and toil of keeping clusters up to date and secure. And then also helping folks explore new technologies that they can use inside their clusters to, keep moving fast and keep taking advantage of some of the really cool things that come out in the space, like AI inference. Anything you want to add there, Andy?
Nope. If you remember one thing, it's that we do Kubernetes, and if you have Kubernetes problems, we can probably solve them. So give us a call.
There you go. So as Caleb said, I'm Stevie. I'm the SRE tech lead at Fairwinds, and I've been there for longer than I could possibly remember at this point, probably going on like 7 years or something. And Andy Suderman?
Yeah, I'm actually going to be 8 years next week, I think, or in a couple of weeks. So yeah, it's been a while. Kubernetes the whole time, so I think the intros were already read, so I'll spare you all the spiel, but yeah.
Because we love it. All right, so we're gonna get into our webinar about running inference workloads on Kubernetes. Before we get started, though, there was one thing that I'd forgotten to ask Andy, because Andy is a drummer, unbeknownst to you all. So he has some musical knowledge, and I meant to ask him as I was researching for this talk, what do you think the AI drummer's favorite beat is, Andy?
I don't know. What would an AI drummer's favorite beat be?
I believe an AI drummer's favorite beat would be an algorithm.
Ooh. That's bad.
AI jokes are not plentiful, and they are, as a whole, pretty bad. All right, so we're going to get into talking about inference on Kubernetes. So I like to level set when we do these things and just get everyone on the same page. So the first thing I'm going to do is really just explain what inference is and why it's different from a typical workload. So most of you, all of you, have probably used some kind of chatbot, LLM, like your ChatGPT, your Claude. And essentially what you're doing when you enter your prompt, what's happening on the back end is an inference. That is, the gears and cogs running in the background to process your prompt and return something to you. The other side of that is the training of the models that do this inference. But what we're talking about is hosting something that will respond, that will use these already created models and respond to your prompt in some way.
I'll be real fast, Stevie. Mm-hmm. I think I'd like to open the polling question real quick
Oh,
for folks while we're going through this.
Yeah.
So we've got a question for you all to answer while we're going through this material here. Would just love to get an idea of how you're currently running inference or utilizing inference in some ways, as Stevie just outlined it. So feel free to throw your answers in there and I'll let Stevie keep going, but love to see where y'all are at on this.
Yeah. Thanks for reining me in.
You're good. You're good.
So I didn't even advance my slide. I'm so into it. Yeah. So what is inference? We already talked about. Why is it different from a standard workload that you would run on Kubernetes, like, a web app or something like that? And that is because of the different stages of an inference pipeline. So an inference pipeline has sort of three basic stages. There's a tokenization stage that runs at both ends of the pipeline. And that's the part that takes your human readable prompt and translates it into numeric data that gets processed. And then at the other end, it takes it does that exact opposite translation. It translates the numeric data into human readable information. And that is a basic CPU bound sort of process. So you can run that part of it on just a regular workload or a node in a cluster. The next step is generally the prefill step, and that's the part that we think of when we're talking about like using GPUs and how intensive an inference workload is. That prefill part is where it takes all the tokens that it created and loads them for parallel processing through the model weights that you've added, that you've pointed it towards, and it uses that to create a big context matrix that it stores in a cache, and that takes a lot of GPU. So that's the really intensive processing part of it. And then the next part is the decode part, where it does like an internal kind of iteration on tokens. So it returns tokens sequentially, taking one token, putting it back through the cache of that matrix, that context cache, to determine what the next token is, using that token to determine the next token, and so on and so forth. And essentially kind of streams that response out to you in a parallel way. And that is sort of memory bound. So at each stage, you sort of have a different resource pressure, a different system pressure, which is different from just a basic workload like a web app, which is generally kind of uniform in the way that it uses resources on a node, right? So it's a different mental model altogether that we're talking about. And on this slide, just sort of put them a little bit side by side. Typical web workload is CPU bound. I should have said also could be memory bound, and generally stateless, right? Like you could have stateful workloads and you like save some data into like a persistent volume or something like that, or some sort of NFS share. But in general, these pods on a typical workload are really just interchangeable. They can all just like scale up, scale down. They have generally fast startup times, which also means that you can be aggressive about your scaling. And they scale on metrics that you're all very familiar with, memory and CPU, which, there are arguments about whether or not that's even stuff you should scale on. And, in general, I think the wisdom, the conventional wisdom at Fairwinds is that you should try and scale on something a little more meaningful, like potentially requests per second or, queue length or depth or something like that, right? But a lot of folks, when they first get started, they scale on basic metrics that everyone understands, which is memory and CPU. Compared to an inference workload, which is, like I said before, it can be GPU bound, it can be CPU bound, it can be memory bound, depending on what stage the workload is in. And that workload has to load your model weights into memory. So that means that the startup time is going to be pretty long in general, especially for first startup. So
some of the demo pods that I've been spinning up over the last couple of weeks for this have taken anywhere from 15 to 30 minutes to start up. So yeah, right. Absolutely. Yeah,
exactly. Yeah. And can you imagine if you were trying to scale those pods the same way you would scale like a regular web app pod? Like it's not really sustainable. As it says, cold starts are painful. there are ways that you can try and mitigate that, which we'll talk about some of the things that we experimented with for this talk. But yeah, so in general, those are some of the differences between the two. Anything you want to add there, Andy?
No, I think you covered it all. It is a very different model from, your average 12-factor web app. So.
Yeah. So so now just a quick overview of like, what is it that your cluster needs when you are deciding that you want to run inference workloads? What are some of the things that you are going to want to tackle? And, we mentioned a bit of these things we're going to before, but we'll go into a little bit more detail with this section, right? So first of all, they're talking about scheduling. The Kubernetes native scheduler doesn't know about GPUs as a resource. It knows about CPU and memory. Those are the requests and limits that help it determine where to put a pod. So you have to have something that essentially sort of extends the scheduler to let it know that GPUs are a thing that it should take into consideration, right? And I think, one of those things could be like it's a device driver plugin. So NVIDIA has one that you can deploy as a daemon set in your cluster that will then advertise that information. Bottle Rocket has an AMI that has that built in, I learned. And so you don't have to deploy it. It comes baked into the NVIDIA AMI. The other part is that when you're running just standard web apps, you can have 3 out of 4 of your web app pods up and serving traffic, and things are still running. But depending on how you deployed your workload, your inference workload to the cluster, you need to have something running that understands the codependency between those systems, right? So if you've decided to do like tensor parallelism, so you're running pods of the same role across multiple GPUs, you need to have something that knows about that concept and will place pods accordingly to get like the least amount of network latency between those pods. Or if you decided to run in a disaggregated way, which means that you're just running multiple instances of the same role. So you're running multiple prefill pods and multiple decode pods, you need to have something that knows about the dependency between all of those pods, right? Because if all your prefill pods come up, but there are no decode pods running, you're not going to get any work. It's not going to, the pipeline's not going to work for you. So scheduling is a major thing to, probably one of the biggest things I think to be aware of when you are preparing a cluster for these things. We talk about resources. We already touched on this, just knowing that GPUs are a different kind of resource and that you have to prep your cluster for knowing that that's a thing that exists. And then you also have to specify how many GPUs you're going to use in your pod spec. GPUs are sort of a singular resource. Like you can use a whole GPU unless you put something like, unless you use an instance that can do, multi-instance GPUs where you can sort of slice them a bit. That gets very complicated though. In general, you just use like one GPU.
Yeah, support for that is pretty early on, especially in all the various Kubernetes abstractions. So
yeah,
not super common.
So being aware that you're going to request resources, GPU resources a little differently than you do memory and CPU. Networking, generally you just throw things into a Kubernetes cluster and networking just does what it does and it's usually fine. But depending on how you've decided to, again, deploy your inference workload, if you've decided to split things up and be disaggregated, then network latency, having things scheduled sort of close to each other, those things are all very important. And another thing is just the fact that the responses that you get from inference workloads they're sort of like streaming, and some proxies will have like timeouts that you have to be aware of that can affect that. And you also will have to probably put something in place like use WebSockets to enable that communication, right? And that's something you generally don't have to think about for your most common, just basic web app workloads, I feel like. And then the last place is scaling signals. And this is a big deal because as we talked about, you don't want to scale inference workload super aggressively, because if you do that, you can have some very slow startup times. Like it can be very painful. And so what you scale on moves from being things like CPU and memory utilization, and moves to being more like things like time to the first token, or the GPU utilization, or a queue depth, and things like that. So you're using different scaling signals for your inference workloads or your inference pods than you would for a typical web app pod. So what we did here, and what we're about to go into next, which is the part that most people are excited about, and that's the demo section. I'm going to start off giving you like an amuse-bouche, if you will, of what an inference workload looks like. Andy's going to follow up with like some past hors d'oeuvres, and then he's going to give you your main course, which is going to be, if you're a meat eater, a delicious prime rib, and if you're a vegetarian, veggie lasagna. I'm very hungry. I don't know if that's coming across. So we're gonna switch over to my screen. I have a terminal running here. We've got like a little demo cluster that we've set up. And this is super simple. So I used, in fact, the thing that I'm running is called VLLM Simple. So I'm using a VLLM chart from their repo, and that chart is it's dead simple and very opinionated in the things that it allows you to do. And essentially, it allows you to load models in, and you can load models by putting in a Hugging Face token and pulling the model. It also has this kind of neat opinionated way of doing S3 loading. So you can preload models into S3 buckets, point the init pod, because there's a init container that's in this pod, to your S3 bucket, and then it will load it onto a persistent volume, which makes load times a little easier subsequently, right? Or makes load times easier in general, right? You just get it from S3 as opposed to loading it live. So that's the way that I decided to do it. So literally, I just have like this one pod running. So I'm not running in a disaggregated way. Everything is contained in this one pod. This one pod's going to do all the work on this one node, and it's a very simple one instance thing that I'm running, and I'm going to copy the command that I use to sort of test it out over here. So you just see that it's working, right? So here I'm doing a curl. I'm port forwarding that the service, the VLLM service, in a different tab. You can see I'm using this model mainly because it was just one that I already happened to have loaded into an S3 bucket. So it was very, I didn't have to do a whole lot. And then here's the prompt, give me one sentence about running VLLM on Kubernetes. I set max tokens just to, and that just tells it how long the response should be or how short the response should be. And I just wanted to keep it simple. It would actually cut it off if it were trying to go longer than that, regardless of whether or not the answer was done. But the way this works out, it actually is fine. And then temperature is about just how far it goes in trying to find matching tokens, how it rates tokens that it grabs from that matrix we were talking about. So if I run this, it just returns a very, not very pretty, but it returns this little sentence about what it is to run VLLM on Kubernetes. That is a very dead simple example of running a demo model in a Kubernetes cluster, and doesn't do much more than this, right? And this isn't something that's super usable. It's just a good proof of concept to make sure that what you need works. Now we're gonna turn it over to Andy because he's gonna show you, I'm using VLLM. Andy's gonna show you a way to do this using Ollama instead.
Awesome. Thanks, Stevie.
Yeah.
So Ollama is an alternative to VLLM, sort of. They're kind of very different from each other, but Ollama is very popular for running locally. So I actually have Ollama running on my laptop. It allows me to work with models locally. Super easy to just say, Olama run, give it a new model name, it'll go pull it, and then serve it up for you locally. So there's a really nice Helm chart out there for doing this in Kubernetes. So basically, I just ran this Helm upgrade install command from this OTWLD Olama chart. Very simple to set up. A lot of values available, but really the only thing I cared about was the tolerations. So as someone asked in the chat, we are definitely using Carpenter here to schedule these. So all the Carpenter nodes come up with a certain list of taints for GPU nodes. We don't want to just be running all of our regular workloads on these GPU nodes because they're very expensive, and we really want to reserve them just specifically for this. So anything that Olama spins up is going to have these tolerations. And when I did that Helm install command, what we got was a very simple Olama pod. And it's sitting here responding to health checks over and over and over again. I am not going to restart it or anything like that because it can take quite a while to get running. But the only other thing I did was then a kubectl port forward to the Olama service. So this is actually already running. Unfortunately, when you're talking about a inference demo, you kind of have to preload everything because of those 15 to 30 minute start times. I don't have time to watch an Olama pod come up, pull a model, start it up and everything. So this is running. I have the port forward running to the Olama service, running on this port here. And what I'll do is just kind of show how I interact with that. So I've been running py.dev via a project called py-less-YOLO, which runs py.dev in a Docker container. All of that being, it's just a agent harness for interacting with LLMs. And so if I go here to my model list, I can search for Olama, and I've got a couple different models loaded into Olama. We can test that by running a curl command against Olama here. So this is the port that I'm forwarding it to. This is the /v1 models endpoint. If I go ahead and run that, we'll see I've got Quen 3.6, 27 billion parameters, and then the 35 billion parameter version running there. So I'm going to select that local 27 billion one, and I'm just going to say, what model are you? And we can watch the logs on this, and you'll see all of the chat requests come through here as the local agent is interacting with it, and we're streaming those responses back. You can see the thinking and everything. So it looks a lot like what you would see from your interface if you're using something like Cursor or ChatGPT or Claude. So that's one example. Olama is very simple in its use case. It's very easy to get running. It's designed to do this. There are a little bit of metrics you can get out of it. They're not in any sort of standard format. So really, I mean, it's kind of like a really simple way to just get something running out there. If I wanted to run my own model, but I don't have the hardware to do it locally, I have a Kubernetes cluster available through work. I can spin up some GPU nodes. That works great. I think right now this is running on a G6 12XL. No, this is running on the G6 8 extra large. So all of these came from this Carpenter node pool that we have. I can show that real quick.
Did you add more nodes to that?
Yeah, so I definitely did add a whole bunch of different node types. So I just want you all to know that I started off with the G4 XL and the 2XL because I was like, I'm gonna keep it like real small. And then Andy came in, he was like, let's go to. Yeah, we're only running them for a few days. It's totally fine. So These are relatively expensive instances. Some of these will get up into the, tens of dollars an hour. So be careful if you're doing this. But the different accelerators available on the G5, G6, and P5 instances are much more powerful than what's available on the G4DN instances. And then when you get into the 8, 12, and 24 extra large instance sizes, you get to multiple GPUs. So you're talking, 4 to 8 GPUs per instance instead of a single one. And I'll talk a little bit about that in a minute. But so Ollama, super simple, but it doesn't really give you a lot of other options. Like, it doesn't necessarily auto scale itself. There are no metrics necessarily available, not Prometheus metrics. So we're kind of missing some things here. Stevie, I think there were some things you wanted to say about that.
Yeah, I mean, you touched on a lot of it, right? So you're using, if you're using like a small model with, a small number of like parameters, and that can fit on a single GPU, then you can, and this is usually for testing, you can run something like what I was running. Like I was, joking, I run an XL or a 2XL, right? That's fine for like a very small prompt, like what I did, and in capping, the tokens as well. But if you're going to start trying to run this in production, then you are looking at, loading larger models that may not fit on one GPU. So then you're going to have to run multiple replicas of your pods if you're doing them like, if you had like multiple VLLM pods, right, you would need to be running multiple of those, like one per GPU. Then you have to think about things like gang scheduling, which essentially means that, I think I mentioned a little bit earlier, with a basic web workload, if 3 out of 4 of your web app pods come up and the fourth one doesn't, you're still Gucci, you're still good, right? Like you can still serve traffic and it's not a big deal. But if 3 out of 4 of your pre-fill pods, don't come up, then you're wasting capacity. They're not doing anything because those 3 pods are waiting for that fourth one to provide, its data. It's part of like a cache or what have you. So, and again, with the scaling, you're going to be scaling on different signals. So you're going to want to deploy things. You're going to want to have metrics coming out of your workloads that can be used in something like I saw someone mention Keta, right? And that is absolutely a good tool to use for scaling these workloads, because an HPA is just basically going to be like CPU and memory, right? And you want to scale on things that are specific to GPUs to inference workloads. So you use something like a Keta to do that. So there's a whole realm of tools and optimizations and preparation that you need to make if you're going to run this at scale, if you're going to run something like this in a production environment. And so what Andy has done is worked with a tool called KAI to sort of show you a bigger, more fleshed out version of doing this. So take it away, Andy.
Yeah. So there's a whole bunch of different projects out there that give you tools to do all of what Stevie just said, right? Which is like all of the complex bits. And there are so many different parameters you can tune all over the place. You could probably make Ollama do all the things you want to do, but there's so many different bits and knobs and options. I'm already showing you like 5 different types of accelerators in this demo, like that we have available to us, and all this other stuff that's going on. And so orchestrating all of that gets kind of complex. So there's a few different systems out there, actually quite a few now, and there's really no, as far as I understand it, no state of the art. Nobody's really won in that department yet, and so I've tinkered with quite a few of them. We actually started out running this demo on Kubernetes, and it works. It does some interesting things. Kubernetes and the whole Ray ecosystem is really big. It goes well beyond inference into training models and running machine learning jobs and basically anything you might want to do in the realm of AI. And so it has so many more options and is infinitely more complex that it's a little bit harder to get running if what your real goal is to run some GPUs, do some inference, and do it in your own environment rather than going to one of the upstream providers. So what we also have going, and I left this prompt running just to kind of show how Ollama is running on this instance, and how quickly it's running, just to kind of get a feel for, token output here and how much it's able to do. There was also some weirdness in the beginning where it got a little confused because I think the context window wasn't quite big enough. And so there's lots of, trade-offs and things that I could tune here. So I'm going to go ahead and kill this, and we'll talk about Cube AI. So moving on from Ray, there's this other project called Cube AI. And what Cube AI is it's just for doing inferencing. The whole project is built specifically for inference. So that's kind of the nice thing, is it's focused, which makes it much easier to get up and running if your only goal is inference. So Cube AI, again, we have a Helm chart that we've installed. So it's a relatively simple Helm chart. You give it a Hugging Face token so you can pull your models from Hugging Face. It also supports EFS caching, which I'll talk about in a second. The main thing you have to do in your install is set your resource profiles. So this comes straight from their example for doing this on EKS. I've modified it a little bit for our environment. But basically, we have all of these different accelerator types, accelerators and GPUs that we want to be able to use. And we're just going to say, we're going to give them a node selector from Carpenter to say, this is how we find that GPU type. So when we request that, Carpenter's going to know to spin up that type. I've added all of the instance types that correspond to these accelerator types into the Carpenter profile. So I think the L4 is the G6 instances, and the T4 is the G4DN instances. So there's a lot of, you got to figure out what accelerators on what instance type, and then there's a whole matrix of how much GPU memory is available on each accelerator type, and how many of them are available. So something to become familiar with is just like instance type to GPU type to number and memory. GPU memory is kind of the big thing here, because I'm trying to run these 27 billion parameter models that in memory are like 24 to 32 gigs of GPU memory usage, and then you need to be able to store context and all of this other stuff. So the amount of memory is a big deal. And so we set these different profiles, and then the other thing I've done is I've set up an EFS store with a storage class in the cluster for accessing it, and that allows Cube AI to cache the model into EFS and then pull it back out of EFS when it starts back up. So it's a little bit quicker on the startup when you're pulling the model cold. So what happens, and I'm not going to be able to necessarily show that today, just because it takes forever, but when you spin up a new model, it will spin up a job that preloads the model into EFS, and then it starts up the model. So we've installed the chart. We have all of our instance profiles. Now we're going to run a model. So we've got, yep.
I just want to say a quick thing that I think is interesting and useful and different between from what Cube AI does with VLLM in that native simple chart. As it can load things from an S3 bucket, for example. That's the way that it prefers you to do it. But you have to manage, you have to be responsible for continuously updating the models in that S3 bucket, right? Because it's not loading it from Hugging Face. And this acts much more like what your typical app workload on Kubernetes is, where there's an image, you just change the image and it goes and fetches whatever that version is. And this is what happens here, is it's going to fetch that latest image and then preload it into the EFS for you, so that you have a cache there, but you don't have to continuously keep track of what's there and load those manually into, or using some sort of script into S3, which is just a benefit of doing it this way.
Yeah, absolutely. And the other thing it does is it kills the cache as well. So when you delete a model, you don't have it in your cluster anymore. It actually goes and drops it out of the EFS cache. So it manages the size of it as well over time.
Nice.
So the Cube AI chart ships with one CRD. It's called a model. You give it a name, you put it in a namespace. I've specified that cache profile because I want it to be cached. It can use both VLLM and OLLAMA. So if there's some, they actually recommend if you're doing CPU-based inference to use the OLLAMA engine, but in general to use the VLLM one for GPUs. And then you've got all your VLLM args. And so this is the other thing. VLLM is infinitely configurable. And it's getting even more so by the day. So when I first started this, it was using an older version of the VLLM image. I actually had to go and override that in my values file to pull the latest one because it didn't have all of the things that the new model I was trying to pull needed. And so that's, VLLM has a ton of configuration. And so this is where we can fine tune the way that the model operates. One thing to note here is that I have specified a tensor parallel size of 4, which means I'm going to try to use 4 GPUs. And so in order to do that, I've said use the NVIDIA GPU L4 profile, but give me 4 GPUs. And so that's going to automatically request, it's going to change that GPU request to 4, which will then cause Carpenter to spin up a G6.12x large in order to provide 4 GPUs to this job. And then the other thing that you might notice here is we have a min and a max replicas. CubeAI is actually capable of scaling down to 0. So you can set this to 0 when the model's not in use. It will turn off those GPU instances. I didn't do that here because if I accidentally kill one of these, we don't have 30 minutes for it to come back up. I've also added this -0 that sort of helps with the startup time. It turns off some of the optimization parameters, but it's still like 15 to 20 minute startup times. So I've pinned this at 1 and 1, but it does do auto scaling of the model. So we'll get into a little bit of how that theoretically works in just a second. So I've applied that model to the cluster. So if I do kgep model, I've actually got 2. I've got this Qwen 2.5, 7 billion struct. That was my testing model because it takes much less time to start up because it's, less than a third of the number of parameters. And if we take a look at the pods that we have running, we have 2 model pods, the Qwen 3.6 and the Qwen 2.5. So if I take a look at the logs for Qwen 3, it's sitting here responding to health checks. That's great. I also have a port forward running on localhost 11.436. CubeAI, for some reason, prefixes all of the API paths with OpenAI, so I had to add that in there. But we can do that same curl call and see what models it has available. Now, that port forward is actually going to the CubeAI pod itself. So this is the interesting bit. The CubeAI pod is what's actually routing the requests to the model. That's how it's able to do auto scaling and scale to 0. So it intercepts the requests and then forwards them to the model pod that should be, serving that particular request. So if we look at services here, we'll see the CubeAI service right here. That is also exporting Prometheus metrics. I'll talk about that in a minute. And then the only other kind of interesting thing that ships with CubeAI is it automatically installs this open web UI. So I have a port forward running to that as well. So we have our open web UI here. This is like an open source AI UI for interacting with different models. You can run this locally. You can run it in a cluster. It does user management. It does state. It does all kinds of stuff that's kind of outside the scope of what we're doing today, but just so you know, it's available. So we can go to the Qwen 3, the 2.5, and we can just go ahead and interact with it here. So how many R's are in the word strawberry? Something is wrong with my Qwen. It worked this time. Okay. Other than the words just strawberry. there's something wrong with the 2.5 model and the way it's running in this cluster. It mangles things. And if I try to prompt it a little bit more, it'll actually get into a fun loop and just totally break itself. So I won't go too much further with this model. You could see it was relatively quick in its production of answers. So it's speedy. Yeah, I'll just send a few more prompts so that, yeah, here we go. Now we start to see it devolve into whatever is happening right now. I haven't had time to look into why this is happening, but you can see the model's running. I'm able to interact with it. I can also interact with it with my local agent here. So if I go back to model and I search for Cube AI, I have both the models available here. So I'm going to switch to the 3.6, the newest Quen model. And we'll give that a look. So this is the same model that was running in Ollama, but I specified that 4 GPU parallelism that VLLM makes available to us. And you can see it's much quicker. It's much snappier at responding. Same responses, generally same quality, but the speed is much higher. We're able to generate tokens much faster. And we can see that in a Grafana dashboard. Because we're using Cube AI and VLLM, we're able to export metrics. So for the Quen 2.5 7 billion parameter model, we have the number of running processes here. We've got our token throughput, so we know how many we're generating per second. We also have time to first token latency, which is an important startup, response metric. And then why did it stop? So are we hitting the end of our, context window? Are we running out of the ability to generate more text? Did it get killed because it got into a loop? Or did we just, finish talking to it, which is kind of the way you want to be ending the conversations, right? And then we can see a heat map of the duration of a request to the prompt length and the generation length. So lots of interesting metrics that come out of this, enabling you to see how your different LLMs are performing. So if I refresh this on the Quen 3.6, this is that last conversation I just had. Similar token output, 31 tokens a second for the prompts. And yeah. So a lot of different things that are available to you in this more complex system that were not available just running Ollama on a single GPU. I think I covered most of the things. Anything I missed here? No? All right. I'm sure we have some questions to get to.
Yeah, absolutely. I mean, that was an incredible walkthrough about using LLM inference on Kubernetes, especially using the EKS environment. So let's go to some of the questions here that we have in the chat. The first one is, what are the differences between a VLLM and Ollama?
Yeah, great question. I think I covered this a decent amount in the demo. Just to kind of like sum it all up, Ollama is great for running locally. It's great for getting started. It's very simple to use. It works great for doing CPU inferencing. If you were trying to run a production grade inferencing system on GPUs, VLLM is going to give you a lot more power and capability to harden that installation, make it highly available, and get metrics and reporting out of it that you might need.
Okay. Next question we have in the chat is, what are some things you'd look at in metrics when something feels slow, but pods are all running?
I think there's, we mentioned some of the, GPU specific or inference specific things that Andy showed in the Grafana graphs too. So like time to first token would be a thing. Generally going back to the basics of resource utilization. So even though, different types, different spots within the pipeline use different resources, and we're focusing on GPU utilization, you can still also look at things, your basic things like your CPU and your memory, right? That all still does come into play. Just not the thing you want to scale off of. So I think you'd be looking at GPU utilization, time to first token, queue depth, and then just basic, other standard sort of cluster and node metrics.
Yeah, one of the things I noticed building the demo is, GPU memory is very often the bottleneck for a lot of these things. But there are a lot of other processes that run using the CPU and memory of the node. However, at least in AWS, the instance sizes are such that the available memory outside the GPU is massive compared to what you might need if you are isolating these the inference workloads like we were in this demo, where it's basically like only the inference workloads run on these nodes. To get better utilization across the cluster, you probably want to enable more things to utilize the rest of that node. But
yeah. That's where disaggregation comes into play, so that you're not, because you can easily have a node that looks like it's doing very little work, like on the CPU, and doing a ton of work on the GPU. So yeah.
Great answers. What's a practical checklist for what we need to have sorted out in our cluster before we even start thinking about what tools to run?
Good question. Stevie, you want to take that one, or you want me to?
I will start, and you can fill in where what you want to add. But I think, again, some of the things that we talked about, you want to think about how you want to run your workload, like how you want to design that. If you want to run it where you're running these discrete all-in-one sort of pods that are running all parts of that pipeline, and just using them across multiple GPUs, or whether you want to split that up and have multiple prefill pods, multiple decode pods, that kind of thing. Like that architectural decision is important. And then from there, thinking about your networking, because depending on how you're running that, you're going to want to take some things into consideration in terms of like what pods get placed where, alongside with other pods. You're going to be looking very carefully at sort of typical Kubernetes primitives, like pod topology constraints and affinity or anti-affinity. And then you're going to want to look at how you want to scale actually, I should step back, because one of the main things you're going to want to look at is what kind of inference tooling you're going to use, what you're going to use to serve the model. So like you're deciding what models you're going to use, you're deciding what tooling you're going to use. As Andy said, you can use VLLM, you can use OLAMA, and then what you want to use to serve that on top, what platform you want to use. So are you using like LLMD? Are you going to use CubeAI? Yeah.
Okay. Well, and speaking of the platforms, if you're a platform owner, where do you split the concerns about owning the platform versus the model/inference tooling?
Yeah, I think that's a good question. So, kind of to elaborate a little bit on the previous question, and then also answer this one, like the best thing that you can do before attempting any of this is good Kubernetes fundamentals. Having an answer for how we're auto-scaling nodes. So we're using Carpenter. We have the ability to add node pools. We have the ability to isolate workloads. We have policies in place and RBAC that enable us to grant access to do certain things and not other things. And we have the ability to control what is created, right? Because if we just unleash, folks onto this, they're going to spin up, a P524XL and be spending $24 an hour in perpetuity, and it's probably going to be like 5% utilized. So having great fundamentals in how you delegate access, what you restrict, what you allow, and then educating your end users on how that works is super important. So all of the basics of Kubernetes and platform and all of the things that Fairwinds does for our customers are still super important to have. as the basis for this. Inference is a new type of workload. It has some interesting bits to it and some differences, but it is still a workload running in Kubernetes. And so we have to have those fundamentals and all of that other stuff in place that we talk about all the time.
Excellent point. If you don't want your CTO spinning up, adding more instance types to your Carpenter node pool, you want to have something in place.
Lock your CTO out of the code is always the right answer. Yes.
Wow, thank you. That's some great information today. You really highlighted some really key importance in complexity of LLM inference. And I think the big takeaway that I'm really understanding from this is that getting from a cluster to a reliable working endpoint takes the right approach of infrastructure, scaling, and of course, operations. So before we wrap up, because just out of time, I want to hand it back to both of you for any final thoughts. And also, how can the audience continue to have this conversation?
Yeah, so, overall, we didn't talk a lot about what Fairwinds does today, but really what we do is we help folks build platforms that provide services like this to their internal developers and to their customers. So if building something like what we showed today, making it production ready and providing it to your internal or external customers is something that you are struggling with or you want to do and you don't know how to get started, contact us, fairwinds.com. There's a link to book a call. Otherwise, you can find me and Stevie both in our community Slack, which is linked on any of our GitHub repos, github.com/fairwindsops. And I'm also in the CNCF and Kubernetes Slacks and available to answer questions there.
All right. Sounds good. And to our audience, thank you for everyone who joined us today. We really appreciate your time. Make sure to keep an eye on your inbox for the on-demand recording. Once again, I'm Caleb Kinchlow. We'll see you next time in future sessions.